Welcome to Chapter 9. So in this section, we're going to look at compound inequalities. But first, let's review linear inequalities and how to solve those. A simple linear inequality looks something like this or this. It looks basically like a linear, a linear equation, except that instead of an equal sign, you have an inequality sign. It might say greater than, this one says greater than or equal to, this one says less than or equal to, or it might just be simply less than. But the solving rules are the same regardless of which direction the sign is pointed. And for the most part, the rules are the same as solving equations. So for example, we want to solve this one for x. Well, you would need to isolate the 2x first by subtracting 11 from both sides. So you would have 2x is greater than or equal to 5 minus 11, which gives you 2x is greater than or equal to negative 6. And then to solve for x, we would need to divide both sides by 2, which would give us x is greater than or equal to negative 3. So that's the solution to this linear inequality. Now in formal notation, of course, you would write it either in set builder notation, which would say the set of all x such that x is greater than or equal to negative 3. Or you could use an interval notation and say that goes from negative 3 to infinity. And you can check your answer by plugging in a point and seeing if it works. So for example, let's plug in negative 3 because that should make this inequality true. If I plug in negative 3, I'd have 2 times negative 3 plus 11. Is that greater than or equal to 5? Well, 2 times negative 3 is negative 6, plus 11 is 5. And yes, 5 is equal to 5, so that is true. And we can also plug in a number greater than negative 3. Let's just go with 0 perhaps. If I plug in 0, let's see if I still get a true inequality. 2 times 0 is 0, so it is true that 11 is greater than 5, so that works, and you get an idea that yes, this is probably the correct solution. Okay, there is one catch that occurs when you're solving linear inequalities, okay, and that is when you multiply or divide both sides by a negative number. So for example, on this one, to solve for x, you would need to divide both sides by negative 5. However, anytime you multiply or divide by a negative number, the direction of the inequality sign flips. So when we do this, what we would have is negative 5 over negative 5 is x, and on this other side, negative 15 over negative 5 is positive 3. Now this inequality sign currently says less than or equal to, but because we divided by a negative number, we're going to switch it to greater than or equal to, so this would be the solution to that equation. Okay, so the big thing to remember here is anytime you multiply or divide an inequality by a negative number, the direction of the inequality sign reverses. Okay, so moving on, what we're going to do in this section is actually solve compound inequalities. So a compound inequality is two inequalities that are joined either by an and or an or. So to see some examples, just scroll down a little. This one says solve 8x plus 5 is less than or equal to 8, or x minus 1 is greater than or equal to 2. Meaning you're looking for all the x's that solve either one or both of these two inequalities. But before we can get into solving compound inequalities, we do have to talk about two things, and that's unions and intersections. So first we'll look at unions. The union of two sets of numbers, remember we talked about set notation earlier, this right here is a set, or for example in the previous problem, this would be the set of all real numbers greater than or equal to 3, that's a set, okay? So the union of two sets of elements is the set of elements that belong to either of the two sets. So if the element is in at least one of the two sets, or if it's in both of the sets, then it is in the union of two sets. And the way you denote union is with this big U, and it's a little flatter than a standard U. Drawn bigger, you would say the union of sets A and B is denoted A union B. So it's kind of a flattened out U here at the bottom. And that means union. It just means the set of all elements that are in either A or B or both. Okay, so let's look at an example. If A is the set of all x such that x is an odd number greater than 0 and less than 10, and B is the set of numbers containing 2, 3, 4, 5, and 6, let's find the set A union B. Okay, so A union B is the set of numbers that's in either one or the other. It's hard to tell what's actually in set A. Okay, set B we can just read it off, but let's figure out what's really in set A here first. Let's just list out all the elements, okay? It's got to be an odd number, which implies that it needs to be an integer. So odd number greater than 0 and less than 10. So that would be 1, 3, 5, 7, and 9. Okay, so then A union B, that's the set of elements that's in either of the two. And let's see, the first, I'm just going to put them in order. The lowest number I see here between A and B is 1. The next number I see is 2. 2 is in set B. Next I see 3. Now 3 is actually in both sets, but you only list it once because it is in the union only once. Next we do have a 4 from set B. We have a 5 in set A, and in set B, it's in both. We have a 6 in set B. We have a 7 in set A, and a 9 in set A. So the set, which is the union of A and B, is the set containing 1, 2, 3, 4, 5, 6, 7, and 9. Okay? So now that you understand what a union is, we can talk more about compound inequalities. So let's describe the set of all real numbers that are either greater than 2 or less than -1, both in set builder notation and in interval notation. Okay, we've done one like this before. The set of all numbers that are either greater than 2, well, we need to give it a variable name so that we can discuss it. So I'll just go with x. That would be the set of all x such that x is greater than 2, or, we would just literally write or, less than 1. So or x is less than -1. So there it is in set builder notation. Okay, now let's imagine this on a number line so that we can write it in interval notation. If x is greater than 2, here's 2, that would be these x values out here. And if x is less than -1, that would be these x values out here. So in interval notation, it would be the lowest number is -infinity, up to -1, not including -1. And what we had done before is we just put either a comma or I wrote the word or, but now you know the union symbol. So technically these should be connected by a big U for union. So union, the set containing all the real numbers from 2 to infinity. So there it is in both set builder and interval notation. And let's do another example. Let's solve 8x plus 5 is less than or equal to 8, or x minus 1 is greater than or equal to 2. So this means find all the x values that solve either this inequality or this inequality. So first we need to solve each inequality for x. So this inequality, to solve for x, we need to isolate 8x, so we'll subtract 5 from both sides, giving us 8x is less than or equal to 3. And then we would divide both sides by 8, which is positive, so the direction of the inequality stays the same. So x is less than or equal to 3/8 on that one. And on this one, to solve for x, we just add 1 to both sides, so we get x is greater than or equal to 3. Okay, notice they're connected by an or. That's very important. So the set of numbers that solve either this inequality or this inequality is the set of x such that x is less than or equal to 3/8, or x is greater than or equal to 3. Now before I box them in as my answer, let's picture them on a number line to make sure that these don't overlap, or to make sure that this can't be simplified or written in a more simple way. Okay, so here's 3/8 is between 0 and 1. So here's 0, 1, 2, 3. Okay, so this is the set of x greater than or equal to 3. We have a closed circle because we're including 3. It's all those numbers. Or the set of numbers less than or equal to 3/8, which would be somewhere about in here. And it looks like these two sets do not overlap at all, so there's no way to write them in a more simple way. So therefore the solution in interval notation would be from negative infinity up to 3/8. And we include 3/8 here, so a bracket, union the set from 3 to infinity, inclusive. Let's do another example. Let's solve negative 3x minus 2 is greater than negative 8, or 5x is greater than 0. So again, we need to first solve in each inequality for x. So we'll start with this one. We'll add 2 to both sides to get negative 3x is greater than negative 8 plus 2 would be negative 6. And then we would divide both sides by negative 3 to solve for x. When we do that, we reverse the sign. Negative 6 divided by negative 3 is positive 2. So that gives us the set of x less than 2. And solving this one for x, we divide both sides by 5. Well, 0 divided by 5 is 0, so we just get x is greater than 0. So it says find the set of numbers that solves either this inequality or this inequality. Okay, let's picture this on a number line, and you may be able to do this in your head without drawing the number line. If you can skip the drawing the number line step. I also want to write this one in interval notation as well. So let's see, if x has to be less than 2. So let's just start with 0 here. 1, 2, 3, 4. X has to be less than 2. Well, here's all the numbers less than 2. That would be all these numbers. Or x has to be greater than 0. Well, here's the set of x greater than 0. You'd have an open circle there, and it would be all of those numbers. Okay, now technically this includes all real numbers because 0 is included, okay, even though I have an open circle there. It's included because 0 makes this inequality true. And although there's an open circle at 2, it's actually included because 2 is greater than 0. So this can be simplified. This would not be a simplified answer here. The simplified version of this would be just to say all real numbers. Or in interval notation, you would say from negative infinity to infinity. Any real number that you pick will solve at least one of these two inequalities. Let's do another example. Oh, actually that's all the examples we're going to do of union. Let's move on to intersections. Okay, the intersection of two sets is the set of elements that is in both sets. Okay, it's where do the two sets overlap, in other words. And it's denoted with an upside down, oops, that is incorrect. It's denoted with an upside down U. It's denoted A intersect B. So the intersection of sets A and B is denoted like this. Okay, for a simple example here, let's again look at something like this. If A is the set of all x such that x is an odd number greater than 0 and less than 10, and B is the set containing 1, 2, 3, 4, let's find where A intersects B. First, let's list out the elements in A again. That was 1, 3, 5, 7, and 9. B is the set 1, 2, 3, 4. So the question is, which elements are in both sets? Okay, the set A intersect B is the set containing, let's see, 1 is in both sets. So 1 would go in this set. 2 is in set B, but it's not in A, so it's not in their intersection. 3 is in both sets. 4 is in B, but not A. And we can stop there because 5, 7, and 9 are not in B. They're only in A. So it's just the set containing 1 and 3. That's where they overlap. All right. In other words, more generally speaking, an intersection sort of means and. It means the set of elements in A and B. Okay, so the big word you should associate with intersection is and the big word that you should associate with a union is or, because that means the set of elements in one set or the other set. All right, so for example, say we want to discuss the set of x, the set of set of numbers x such that x is greater than 3 and x is less than or equal to 5. Okay, first let's draw that on a number line. Now remember, both of these inequalities have to be true now, not just one or the other, but both must be true. So drawing this on a number line, we just need to include 3 and 5, so let's go for 2, 3, 4, and 5. All right, x has to be greater than 3 and less than or equal to 5. So it must be in between the two numbers. That's the only way you'll get an x number that actually makes both of these inequalities true. Now there's a shorthand way to write an intersection of two sets, or when you're combining two sets or two inequalities with an and, there's a shorter way to write it. More commonly what you'll see is what's called a double inequality, where you describe it without the word and. Okay, to explain how we get there, I'm going to first flip this one around. If x is greater than 3, that's the same as saying 3 is less than x. Okay, this one I'm not going to change. So 3 must be less than x, and x must be less than or equal to 5. In other words, what you could say is x, put in a big X in the middle, and say x must be less than or equal to 5 and greater than 3. Now notice these two inequalities point in the same direction. They're both less than signs. Because otherwise this inequality would not make sense. Okay, it only works if both inequalities point in the same direction in order to write it like this. So this is the compact notation for an intersection of two sets that are intervals of real numbers. Let's look at another example here. Let's solve for x, the set of all x, such that x plus 3 is less than 8 and 2x minus 1 is less than 3. So as before, we first solve each inequality for x. Subtracting 3 from both sides on this one gives us x is less than 5. This one will first add 1 to both sides to get 2x is less than 4. Dividing both sides by 2 gives us x is less than 2. Okay, so x must be less than 5 and x must be less than 2. So let's draw that on a number line. Although you might be able to picture it without drawing it, that would be fine. Okay, if x is less than 5, that would be all of these values. But x also has to be less than 2. Well, here's the set of x that is less than 2. So the only set of x's that are in both sets is where these two sets overlap, which is from here to here, right at 2. Okay, that's the set that's in both sets. So this can be written more compactly as simply the set of all x such that x is less than 2, or an interval notation from negative infinity to 2, non-inclusive. Let's look at another example. Let's solve 4x is less than or equal to 0. That one's simple. Divide both sides by 4. X is less than or equal to 0. Solving this one, we first subtract 2 from both sides to get 3x is greater than 6. Divide both sides by 3 to get x is greater than 2. Okay, now notice they're connected with an and. So x has to be less than or equal to 0 and x has to be greater than 2. Let's picture that. So here's 0, here's 2. X has to be less than or equal to 0 and x has to be greater than 2. Well, that's not possible. These sets don't overlap. It's not possible for a number to be in both sets. So therefore, this actually has no solution. And that's because these two sets do not overlap. A number cannot both be less than or equal to 0 and greater than 2. Let's look at another example. This one is actually already written in the compact notation as a double inequality with an x in the middle here. So we're going to solve this inequality for x. First, we'll need to subtract 5 from both sides to isolate that x here. So actually, it's not both sides, it's from all three sides. Okay, 5 minus 3, or 3 minus 5 is negative 2. That's less than, 5 minus 5 is 0, those cancel. It's less than negative x, which is less than 9 minus 5 is less than 4. Now to isolate x, we need to divide everything by negative 1. When we do, both signs will reverse. So we'll get negative 2 over negative 1 is 2. That less than becomes a greater than. The negatives cancel. We have x. That sign reverses. And 4 over negative 1 is negative 4. Now this is a strangely written double inequality because of the direction of the signs. Although it's true, it doesn't make as much sense to read 2 is greater than x is greater than negative 4. What makes more sense is to reverse the whole thing and say that's the same as saying negative 4 is less than x, which is less than 2. To me, it makes more sense to look at it in this order because this number is lower than this number. Okay, so what this is saying is that's the set of all x greater than negative 4 and the set of x such that x is less than 2. So you have negative 4. That would be the set of numbers in between them, essentially. Okay, so in interval notation, that would go from negative 4 to 2. Now, on one like this, I think it would be a good idea to check our answers. Okay, let's plug in a number in between negative 4 and 2. Let's say 0. Let's plug in 0. If we plug in 0 into this inequality, we'll get 3 is less than 5 minus 0 is less than 9. Well, 5 minus 0 is 5, so that just goes away. Is that a true inequality? Yes, it is. 3 is less than 5, and 5 is less than 9, and 3 is also less than 9, which has to be true as well. So that does work, and there's our answer. And let's do another one like that. Solving this double inequality for x, first to all three parts, we need to add 1. So negative 4 plus 1 is negative 3. It's less than or equal to x over 2. It's less than or equal to 4. Now we multiply both sides by 2. However, it's just positive 2, so no signs get reversed here. So negative 3 times 2 is negative 6. That's got to be less than or equal to x, which is less than or equal to 8. So 6 must be greater than or equal to 6 and less than or equal to 8. That does make sense. And I'm going to skip drawing the number line this time and just go straight to interval notation. That means x must be from negative 6 to 8 inclusive because we have an equal sign on both ends here. That's it for section 9.1 and compound inequalities. Tune in next time for 9.2.